Greetings, mathletes, and welcome back. Today we're going to be talking about limits that involve infinities. So infinity could be our answer, or it could be the value that x is approaching. And we're going to see how to deal with those things. Now, I could go through and focus on the theory and whatnot, but I think really where students have more of a problem is with the algebra, because there's a lot of weird little tricks that you do, things that maybe you didn't even realize were legal to do. And so we'll take a look at those. And what I'm going to do is just kind of arm wave at the theory side of things along the way so we get an idea of how this works. Now, I want to point out before we get started here that many of the things that we're going to be learning ultimately will be applied to graphing functions, right? A lot of the calculus really does apply to graphing functions. So that is going to be one of the things that we will do with these, but not today. So you will hear me talk about asymptotes, and I'll do little sketches showing you what that part of the graph looks like when this happens. But by and large, we're not going to be graphing the functions themselves. So in any case, let's go ahead and get started here. Okay, so the first limit I want to look at is the limit of 3x over x minus 1 as x approaches 1. Okay, so we've seen things that look like this before. There's a difference now, though. The big difference is that this discontinuity that's being caused at x minus 1 isn't removable. In the past, they've been removable. There's been some algebraic trick I can do to get rid of it. Now, when you have a discontinuity like this, that's at a set number, right? Like in this case, it's at 1. There's actually 4 possibilities of what might be happening there. So, let's just say this is the discontinuity here. You may have something that does this, right? They go opposite directions. You may have something that goes the other opposite directions, meaning this way, right? Really, it's just they go opposite or they don't. If you have either of these cases, the limit does not exist, right? Because they're not going to the same place. The left hand and the right hand limit don't match. The other ones either will both go up or both go down, right? I'm just going to... And this case, right, either if they both go up or if they both go down, they are heading the same place, in which case we would say that the limit is either positive or negative infinity. And so that's really what we're trying to dice out most of the time. If we have a discontinuity that's not removable, what we're trying to figure out is it going different directions like this, or are they going the same direction? If they're going the same direction, which direction? And that's my limit. So that's what I'm going to try to figure out here. I know I have an asymptote one way or another because of that discontinuity. So I'm just trying to figure out which kind of asymptote I have. So looking at this thing, one of the things that we can tell is that there's a problem at 1. So let's say this is 1, right? We have some kind of asymptote here. So really what you can do is just check a point on the left and check a point on the right and see if they're going up or if they're going down, because we know they don't cross the asymptote at 1. So just reasoning this out, let's suppose x is just a little bit smaller than 1. So we're going to look at the limit as x approaches 1 from the left of 3x over x minus 1. We'll figure out which way it's going, and then we'll look at it from the right and figure out which way it's going and go from there. So if I'm going from the left, that means the numbers I'm choosing are just a little bit smaller than 1. So if they're smaller than 1 and I subtract 1, that makes it negative, right? And if it's a number that's just a little bit smaller than 1, that number is positive. And so here's what I'm doing, is I'm looking at what happens with the signs when I plug this in. So since the discontinuity is at 1, I can look at numbers between 0 and 1, which are all positive, and I can look at numbers between 1 and 2, right? So I'm looking at either side of this thing is what I'm actually doing. And if I look just to the left of 1, I get a negative on the bottom and I get a positive on the top. Well, that means if I have a positive divided by a negative, that means it's going down, right? And you notice I'm just reasoning this right now. I know there's an asymptote already just because the discontinuity is not removable. So it's really just a matter of figuring out what it's doing on both sides. So this thing, as it gets closer to the 1, stays negative, which means it has to keep going negative, because if it turns around, it's going to be positive at some point. So what that means, let me get these guys off of here. And you notice we didn't do any math. We just reasoned this out. If I approach from the left, I go to negative infinity. So now we need to look at it from the right. And again, it's just going to be a reasoning thing. I'm going to approach 1 from the positive side. And if I do the same thing, so I know I'm dealing with all positive numbers. I know this numerator is going to be positive because I'm sticking in a positive number. The denominator, now if I take a number that's a little bit bigger than 1 and subtract 1, I still get a positive number. So I end up with another positive here, which means that the numbers on the right-hand side of this are going to be positive. So that means that this thing is going to approach infinity, or approach positive infinity, which means that the other side of this is going up in this case. So we have these things going to different infinities, which means that the limit, the overall limit, this guy, does not exist. Okay, so you do have to consider the limit from both sides when you're looking at these asymptotes, these vertical asymptotes. Okay, so now I want to take another look at this function. I'm going to change this function just a little bit so we can see the other case. Yeah, so let's do this. We'll go ahead and erase this. Go there, and then that. And we'll just do that from here. Okay, so we are going to change this function now and reevaluate it. And I'm only going to change it in a small way. I'm going to take this denominator. Actually, I think I should rewrite it, otherwise it's going to get too cluttered. Okay, so it's 3x over x minus 1 squared. So this time I'm squaring the denominator. Now, again, this is a reasoning thing. So we have to take the limit of this guy as x approaches 1 from the negative side and from the positive side. I'll just put quotes. It's the same function. Okay, so if we come in from the left-hand side, we have the same kind of deal again, right? So here at 1, let's look at what happens on the left. So if I plug numbers in that are just a little bit less than 1, what I get up here in the top, it still is positive, right? Because really you only have to consider the ones that are really close to 1. Down here in the bottom, you notice it doesn't matter. It actually doesn't matter what happens here. The square is going to make everything positive again. So I'm going to end up with positives on both of these this time. And because of that, and because the x minus 1 is still not removable, this comes out to positive infinity, right? So what that means is that this function goes up on this side. All right, now we're going to look at the same function again, but this time from the right-hand side. Actually, I should have just rewritten the whole function. I'm going to do it anyways. 3x over x minus 1 squared. Okay. Now, if I pick numbers that are bigger than 1, those are all going to be positive. So when I multiply it by 3, I get a positive number. And over here, I'm still squaring it, so I also get a positive number. This time, they both approach positive infinity. Since they're going the same direction, right? They're both heading upwards towards that asymptote, and they're both heading towards infinity. It's the same infinity. This time, one isn't positive and one isn't negative. That means the limit does exist, and it's infinity. right? I know we've been saying it does not exist at this point, but it does, kind of. So in any case, that's how we're going to deal with this stuff. Now, keep in mind, sometimes you have polynomials. You can remove some of the discontinuities, but not all of them. So if that's the case, it's just a matter of figuring out what happens at those discontinuities. Okay, now, so let me go ahead and clear this off. And I want to look at this one more time. Okay, and I think I'm going to change this. I'll just do this. There we go. Okay, so I'm going to look at the same function one more time here. So let's look at the limit of 3x over x minus 1. Okay, this time we're not going to take a look as the limit goes to 1. We're going to take a look as the limit goes to positive infinity. Okay, now we have a little bit of a problem here because if you look at the two functions, the ratio here, the numerator goes to infinity, right? Because as x goes to infinity, 3 times x is going to go to 3 times, well, it's going to go to infinity. And same thing with x minus 1. X minus 1 goes to infinity. So both of these values go to infinity, but the ratio may not. So here's the trick we use to get a hold of this. We need to massage this so we can get terms to go away. So here's what we do. I'm going to take the function 3x over x minus 1, and I'm going to multiply the top and the bottom by the same number, 1 over x. Now I chose 1 over x because x is the biggest term, the highest degree term. And that's basically what you end up doing. It's 1 over the highest degree term each time. So if I do that, I can change my entire function to 3, well, let's write it this way just so it's more clear. 3x over x, right? That's the numerator, over x minus 1 over x. Don't forget to distribute to all the terms. Now, if we look at the limit this way, right, if I simplify this, that 3x over x is the same as 3, x over x is the same as 1, right? That cancels, becomes a 1. And then 1 over x doesn't reduce, right? And this is still as x goes to infinity. But let's think about what happens. This is actually kind of useful. What happens to 1 over x as x gets bigger? If I look at the limit of 1 over x as x gets bigger, the bigger x is, the smaller this whole thing gets. So this actually goes to 0. And so this is the notation we use. These guys aren't going to change because there's no x next to them to change their value. This one, we just write it this way. It goes to 0. And if it goes to 0 and there's nothing left to plug anything in with, this is 3 over 1, or the limit is just 3, which is actually kind of cool, right? So that means that the limit of this guy, right, as x goes to infinity is 3. Now, what that means for the graph is that we have a horizontal asymptote at 3. So if I were to graph this function, and we would have to plug in values to know exactly what it's doing, but I know I have an asymptote at 3, right? So that means the function is, whatever it's doing is either going to approach this value from the top or from the bottom. And I want to mention something else about asymptotes, because a lot of the time there's a misconception. If I have a line that's an asymptote, there's often this misconception that you're not allowed to cross an asymptote. That's not true. An asymptote just means that even if it crosses, it has to get closer and closer without getting farther away again, right? So it has to keep getting closer. So there are asymptotes that actually get crossed an infinite number of times as long as they get closer and closer to the line, right? If you can cave them in here, if you can sandwich them in, and force them to squeeze down to a single point, they still have an asymptote there, right? So you can cross asymptotes. It's just the ones that you've seen up until now you probably haven't crossed. Okay, so that was the trick, right? And that trick is just multiplying by that reciprocal. Now, negative infinities are kind of interesting. So I want to look at the exact same function one more time. We've really diced this function out pretty good, haven't we? And we're going to look at the limit as x approaches negative infinity this time. Okay, well, if it's going to negative infinity, well, if we think about this, if x goes to positive infinity, that means that if I have a negative x, that goes to negative infinity. So what I can do is swap out a negative x for x and change this infinity to positive. And so that's what I'm going to do. So I'm going to change this limit. I'm going to substitute negative x's in for all of the x's. And make this 3 times negative x over negative x minus 1. Now you notice that does change the function. Oh, it's not negative infinity anymore. Sorry. That should be positive infinity because I substituted in the negative x, which means that it's now going to go to negative infinity. Okay. So let's see, where did I go? That's what I needed. Okay, so it's limit. So this is now the limit as x goes to positive infinity of negative 3x over negative x minus 1. Well, we can play with signs if we want. If I want to, I can just do this. Oh, that's negative. And then I'll go x plus 1 down here by factoring out the negative and cancel those. So we'll do the limit as x approaches infinity of 3x over x plus 1. And that's an algebraically equivalent. It's an algebraically equivalent statement. So this limit is going to be the same as this limit up here, right? These guys are the same because I just manipulated the algebra a little bit. Excuse me. Okay, now what we need to do is the exact same trick we did before. We're going to multiply by that 1 over x over here. Right, so I'm going to get rid of these guys. And we want to just multiply by 1 over x and see what happens. So this ends up changing it to 3x over x over x plus 1. Oh, excuse me, plus 1 over x. So it's very similar to last time, right? So those will cancel, that cancels. And so this is going to be equal to the limit as x goes to infinity of 3 over 1 plus 1 over x. 1 over x, as I go to infinity, is going to go to 0. And if that's true, I get the exact same limit again of 3 over 1. Right? Keep in mind, those limits aren't always the same when you go to positive or negative infinity. Sometimes they switch. What really ends up mattering is whether or not the rational expression you're looking at turns out to be an odd or an even function, right? If it turns out to be, actually, let's actually, boy, I said actually like 15 times just now. It depends on whether each of these individual functions are odd or even, or neither, right? And so that may change things. So you might want to pay attention to that. The other thing I want to point out too is as we go through this, there are shortcuts to this. So if you notice patterns, see if you can verify the patterns. Because if you can, then you're legit to use it as a shortcut. Okay, so now let's diversify our examples. We've looked at the same example like, I don't know, what, 4 different ways now? So let's go ahead and expand that a bit. There we go. Okay, so let's go ahead and take a look at something that at least on the surface, looks a little crazier. No, I want black. Okay, let's say we have the limit as x approaches infinity of 3x to the 7th plus 5x squared minus 1 over, what is crazy stuff, 6x cubed minus 7x plus 3. Ooh, good stuff right there. Okay, so it does look a little bit crazy. But, without factoring, without anything else, we're talking about a limit at infinity. First of all, if you're talking about a limit at infinity, as x approaches infinity, there's no removable discontinuities that are going to matter right now. So you can attack the function exactly how it is. Now, with something like this, like the previous example, we multiplied everybody by 1 over x, right? The reason for that is that x was the highest degree term in any of the polynomials involved here. In this case, the highest degree term is 7, right? We have that x to the 7th there, right up here. So here's what we're going to do. We're going to use that to our advantage. So I'm just going to pull the expression out and kind of revamp it. Over 6x cubed minus 7x plus 3. Okay, so what we're going to multiply by this time is 1 over x to the 7th, right? And so whatever the highest exponent is for your variables, it's 1 over that you're multiplying the top and bottom by. Right? Remember to distribute across all terms. That makes a huge difference. Okay, so let's rewrite this now and see what it looks like. So I have 3x to the 7th over x to the 7th plus 5x squared over x to the 7th minus 1 over x to the 7th. And then in the denominator, we have 6x cubed over x to the 7th. Yes, this is a lot to write. Minus 7x over x to the 7th plus 3 over x to the 7th. Okay, so now let's simplify all these terms. So that cancels completely. So this actually, and I'm going to write it over here. So the first term would be 3, and then let's see, that's x squared over x to the 7th, so that would be plus 5 over x to the 5th, minus 1 over x to the 7th. And then down here, I have 6 over x to the 4th, minus 7 over x to the 6th, and the last thing is plus 3 over x to the 7th. Woo, that's good stuff right there. Okay, so if we're looking at this limit as x goes to infinity, right? Let's see what we got here. So 3 sticks around, right? There's no x's there, but this goes to 0. This goes to 0. This goes to 0. This goes to 0, and this goes to 0, right? Because as x gets bigger, those terms get closer and closer to 0. So really what I end up with here is a 3 divided by 0, which is undefined. And if I'm getting an undefined value, what that means is that the limit does not exist, right? So this, well, I'm making a mess here, but this final limit does not exist. And that's because I can't get a defined value, right? This thing actually does blow up to infinity as you get closer and closer to infinity. So that's good to know too. That means it doesn't settle on a value. It just keeps getting bigger no matter what, right? It keeps growing as x grows. Okay, so that happens. Now let's take a look at another one here. All right, so let's say we have, well, let's say we have lousy handwriting, which I do. Okay, so we want the limit as x goes to infinity, and this time we're going to do this a little bit differently. let's say I have 3x cubed plus 5x plus 2 over 4x cubed minus 6. Okay, so again, we're looking at a limit as x goes to infinity. So that means I don't really care about any removable asymptotes. It's really just a matter of taking this and figuring out what to multiply by. Oh, that's a cube. Minus 6, and again, the highest exponent in here, the highest degree is 3, which means we're going to multiply by 1 over x cubed. Right, and that's going to change my function to 3x cubed over x cubed plus 5x over x cubed plus 2 over x cubed over 4x cubed over x cubed minus 6 over x cubed. Okay, so let's go through and see what we got here. So these will cancel. Yeah, let's just rewrite everything. So that'll cancel and give us a 3. The next term over, one of these x's will cancel, so I have plus 5 over x squared plus 2 over x cubed. And then down here, that gives me a 4 and minus 6 over x cubed. And we're still looking at that limit as x goes to infinity. So let's see what the terms do. Okay, so this one goes to 0, right? Because as x gets bigger, that term gets smaller. That one goes to 0, that one goes to 0, and that one goes to 0. And look what I'm left with. I'm left with 3/4 this time. Which means the limit does exist, and it settles down at 3/4. So this one has an asymptote at 3/4, a horizontal asymptote, right? It's kind of interesting. You know, you'll notice as we go through these things, sometimes they have, sometimes they go off into infinity. Sometimes they settle down into a nice ratio like this, or just a regular number, like 2 or 5 or something like that. And sometimes the entire thing goes to 0. Okay, so it would be really interesting to see if you can figure out what the cases are that make them do those different things. I'll give you a hint. If what it ends up having to do with is the degree of the numerator and denominator. So as you go through your homework, see if you can see a relationship between the degree of the polynomials that you're taking a ratio of and what kind of answer you're getting. Because there is a relationship between those things. It would be real neat to see if you can figure those things out. Okay, next. So let's see, let's do this. I want to take a look at the exact same thing. This time we're going to switch from approaching positive infinity to approaching negative infinity. And we're going to see where it goes, see what happens. Okay, so in this case, I want to look at the exact same thing, but instead of positive infinity, I want to see what happens at negative infinity. Okay, so if we want negative infinity, basically what we do is we still look at the limit as x goes to positive infinity, but we substitute a negative x for all these x's. So let's see what we get here. If I substitute negative x, that's going to be 3 times the cube of negative x plus 5 times negative x plus 2. And then we have 4 times negative x cubed minus 6, right? So those are our two things. Let's just simplify that. That gives me negative 3x cubed minus 5x plus 2. So it's changing the function. And minus 4x cubed minus 6. Okay, so that's what we're looking at now. So we got negative 3x cubed minus 5x plus 2 over negative 4x cubed minus 6. Okay, so that's what we're looking at. Now, looking at these two terms here, I think we can see that it's going to be the same thing. I'm going to multiply top and bottom by 1 over x cubed. Right? And if I do that, I'm skipping a few steps this time, but you can verify this. What that'll change my limit to is -3 plus, minus, watch those signs, minus 5 over x squared plus 2. And then, oh, sorry, not 2, 2 over x cubed. There we go. And then in the denominator, that'll be -4 minus 6 over x cubed. Right? So anything with a constant in the numerator and a variable in the denominator is going to go to 0. Right? So all those things go to 0, and what that leaves me with is -3 over -4, and a negative divided by a negative is a positive, and so I get 3/4 again. It's kind of cool, actually. It's a lot of work, though. So you have to be patient with yourself. Be okay with the tedium. It's just a matter of getting through it. I also want to warn you, a lot of the time with these problems, you'll start, but you don't see the whole plan, right? You can get yourself up to a certain point, and then you have to work through that certain point. That's okay. That's actually part of the process. So be patient with yourself as you're working through these. And then if you really get stuck, come and talk to me or talk to your neighbors. Talk to your classmates. Nobody's sitting by you right now. So in any case, let's go ahead and move on here. I want to take a look at what happens with some of these trig functions. So let's go ahead and clear this out. Okay, so first off, I want to bring up this limit again. It's not actually the same limit. It just looks like it. Oh. There we go. Let's try this again. Okay, so if we're looking at sine x over x, right, and before we were taking its limit as x goes to 0, and we found out that that was equal to 1, okay? Now, I want to talk a little bit about what happens when I take x to infinity instead of to 1. Okay, so this is one of those places that, one, I have to talk a little bit about what it means to multiply something by sine. And also it has to do a little bit to do with that sandwich theorem too. We talked about it before, but it's coming back up here. So the idea with sine x over x is sine x over x is the same thing as 1 over x times sine x. Now you notice this 1 over x is in the same position that the amplitude would be, right? If I was looking at 3 sine x, then what that would mean is that sine is bounded by 3, right? 3 is the amplitude. Well, when I multiply a function by sine of x, this function basically becomes the new amplitude. So like let's generalize it a little bit. If it's f of x times sine x, what that means is whatever the height of f of x is the amplitude of sine at that point. So if f of x happens to be something like x squared, right, I'd have a parabola. And sine would actually be bounded by the positive and negative parabolas here. That touches 0. Right? So it'd get bigger and bigger and bigger. Well, 1 over x doesn't get bigger and bigger and bigger. It gets smaller and smaller and smaller. And so that means the amplitude is getting smaller and smaller and smaller. And matter of fact, the graph of sine, or the graph of 1 over x, if I look at this, looks kind of like this. Right? Now, because it's an amplitude, that means I have to bounce around between the positive and negative. So that means that this top part ends up being reflected on the bottom, like so. Right? So what that means is that sine, we actually already know there's a hole right there at 1. But whatever happens after that, sine ends up being trapped between those two boundaries. And 1 over x, we've already been using this as 1 over x goes to infinity, or as x goes to infinity, 1 over x goes to 0. And so that means the sign of 1 over x, or the sign of x over x as x approaches infinity, goes to 0. Right? Really, what we just did by drawing this picture, we said, well, the sign of x has to be, has to be between 1 over x and x. And since this goes to 0, and this goes to 0, and this has to always be between it, that means, oh, sorry, sine x of x over. There we go. Sine x over x also has to go to 0. Now, you can make, because of this picture here, you can make the same argument with cosine. And so that means that the limit as cosine, the limit of cosine x over x as x approaches infinity is also equal to 0. Now, because of that, that means you get 0 in both directions. You can see it from the drawing here, right? I can see that as I go off to negative infinity, I'm going to get 0 as well. But you could do that substitution of negative x, so you can see it comes out the exact same way, right? Okay, so that's the result that I want you to remember. I want you to remember this, that sine x over x, if I take the limit as x goes to infinity, I get 0. And the same is true with cosine. Those are the only two trig functions that works for. Okay, things like tangent, secant, cosecant, you have to turn them into sines and cosines and then deal with sines and cosines. Okay. Okay, so now that we have that piece set down, actually, let's just do this. Control A. There. Let's go ahead and apply that. Stop that. Okay. So let's look at something that, at least at the onset, looks kind of nasty. Let's look at the limit as x goes to infinity of 2 minus t plus sine t over t plus cosine t. Right? Now, I have shown you all the tools that you actually need for this. There's no new tricks we're going to be using. Pause this and see if you can put it together. It might take you a little while, but it'll be worth the struggle if you can do it. And it's actually worth the struggle if you can't do it too, because then you're thinking real hard about what the solution is when you watch the solution. So go ahead and pause it here and see what you can work out. Then we'll walk through it together. So I'm assuming you've paused it. Now, there are more than one trick. There are more than one trick. There are many tricks. There we go. There are many tricks to actually solve this. I know the most direct one, but if one of you came up with something other than this, I would love to see it and see, we could probably both learn something new. But the standard trick for something like this is the same one that we used with the polynomials. You have a sine and a cosine here. And I know if I have like a sine of t over t or a cosine of t over t, those go to 0 also. So what I'm going to do is multiply top and bottom by 1 over t, because, that's the highest exponent. And so I really am treating it a bit like a polynomial. And so that's going to change our entire limit to 2 over t minus t over t plus sine t over t. And then down here at the bottom, I have t over t. Let's see here. There's only two terms. Plus cosine t over t. Okay, and if we look at each of these things here, let's see, that one goes to 0. That goes to minus 1. that goes to 0, that goes to positive 1, and that goes to 0, right? So basically what we end up with if we write all that stuff down is 0 minus 1 plus 0 over 1 plus 0, which ends up being negative 1 over 1, which is negative 1, right? So we have a limit here at negative 1. It's kind of cool stuff. If you wanted the negative 1, and this is one of those ones that when you plug in the negative, right, one of the things you end up doing, because you want it to be back in terms of t again, you can handle the negatives with the polynomial terms, but the sign, if I end up plugging in a sign of negative t, remember sine is an odd function. That's the same thing as the negative sine of t, right? So I can, with sine, I can pull the negative out. If I have a cosine of negative t, that's the same thing as cosine t, because cosine is an even function. So these two identities, the even and odd identities of sine and cosine, are very useful so that you can have t's in here instead of having to deal with negative t's. Okay, so that's probably the main thing you'll have to do with sines and cosines. When it comes to tangent, secant, cosecant, all those other ones, cotangent, you end up turning it into sines and cosines and then trying to get a sine t over t in there somewhere. Yeah. Okay, so let's go ahead and take a look at some other stuff here. Okay, so the last couple examples that we're going to look at here, they're really just algebraic things that, well, they don't look normal, so I want you to see them before we actually have to deal. So let's turn the pen back on. So let's say we're taking the limit as x goes to infinity of the cube root of x minus the fifth root of x over the cube root of x plus the fifth root of x. Right? What do you do with that? That seems very odd. So, well, let's see what we can do. Let's see, probably the first thing I would do is rewrite these so that they are exponents. Right? So this is x to the 1/3 minus x to the 1/5. Now I know my first thought when I looked at this was that you're going to use a conjugate. That is actually, it's not a bad idea, except it doesn't work because the conjugate, multiplying by the conjugate only works if you have square roots, and these are different roots. So now that we have exponents here, it's really a matter of just figuring out what we can do with them. And it turns out we use the exact same trick we used when we had a ratio of polynomials. So the tough part is deciding which of these terms is the higher degree, right? But 1/3 is a bigger number than 1/5. So that's our higher degree. So what we're going to do is multiply top and bottom by x to the, 1 over x. Let me try that again. So 1 over x to the 1/3 is what we're multiplying top and bottom by. Now this gets a little bit messy. There ends up being a lot to keep track of here. So really, as you're going through this, when you work out problems like this, you want to have a little scratch area to work things on, so you can just put your results back down into the next step. If you put all that little scratch work in there, you're going to lose track of this problem. Okay, so multiplying this in, and I'm going to leave a lot of the in-between steps for you here. Let's see, x to the 1/3 divided by x to the 1/3 ends up being 1. Here I end up with, it's minus, I have x to the 1/5 over x to the 1/3, which means I'm going to be subtracting the exponents, which means that this is now 1 over x to the 2/15. Okay? Now, down here in the denominator, when I multiply this through, I get the same thing. I get 1, but it's plus 1 over x to the 2/15. Now I switched those to exponent, or I switched those roots to exponents so that we could actually do this arithmetic. It doesn't work so well with the roots themselves. Now that we're in this position, and this looks a little bit weird, but keep in mind that x to the 2/5 or 2/15 is the 15th root of x squared, right? That's actually what that means. So looking at this, well, the 1 doesn't change, but as I go to infinity, this goes to 0 and this goes to 0, which means that my limit ends up being 1 over 1, which is just 1. So there ended up being a lot of little scratch work, and you're going to find that as we go through the semester, that does increase. So your algebra is going to get really, really tight as you go through this semester because you really have to keep track of things. It's really easy to miss stuff. Okay, now let's look at our last tricky example. Okay, again, we end up using the same trick, but we have to do some work to get to the point where we can make that trick, where we can use that trick. Okay, so the last example, where did it go? There it is the limit as x approaches infinity of the square root of 4x squared plus 1 over x plus 1. Now, looking at something like this, if the whole thing had been in a root, and this is actually how my thought process went, if the whole thing was in a root, I could take the limit of what's inside the root, right? And then once I get an answer there, I'll just take its square root. And that's one of those limit rules we had, that if I have a square root and a limit, I can take the limit of what's inside the square root and then apply the square root to it afterwards. So that's what I'm going to do, but I have a problem. Only part of this is in the root. So now we're talking about x approaching positive infinity, which means that we're sticking positive numbers into this. Okay, one of the things that you can do if you have an absolute value, and actually you can do this with anything almost. I don't have to limit it to an absolute value necessarily, but if I have x plus 1 by itself, I can rewrite this as the square root of x plus 1 squared, right? And it works because we're only dealing with positive values, because if x plus 1 ends up being negative, when I square it, it makes it positive, and then I take the square root, and that's positive also. So really, when I take the square root of a square, I'm taking its absolute value. That's actually one of the definitions of absolute value. And it is how we're going to deal with absolute value here in calculus, as you switch it over into this function and deal with it from there. The only reason I can take this liberty is because we're going to positive infinity, so I know we're going to have all positive values anyways. So I'm going to rewrite this as the square root of 4x squared plus 1 over the square root of x plus 1 squared. And what that means is I can join these guys together into a single root as 4x squared plus 1. And now, because I'm going to need to anyways, I'm going to square out this x plus 1, right? Because I'm joining both of them. The x plus 1 squared ends up being x squared plus 2x plus 1. Excuse me. So all we really have to do is take the limit of this inside. So here's what we're going to do. We're going to take the limit. We're going to take the limit of 4x squared plus 1 over x squared plus 2x plus 1. And then when we're done taking that limit, we're going to take its square root, right? And so we'll take the square root of the whole thing afterwards. And since this is just a ratio of two polynomials, I can use that 1 over x squared trick. And so that's what I'm going to do. I'm going to multiply by 1 over x squared. And it has to be the same thing you're multiplying on both. So that will give me, this is now the limit of 4 plus 1 over x squared over 1 plus 2 over x plus 1 over x squared. You notice I took out all the simplification and stuff like that. I'm leaving that for you from here on. Now, if I look at this guy, when I take this limit as x goes to infinity, that goes to 0, that goes to 0, that goes to 0. And so what I end up with is 4 over 1, right? So what we actually want for this whole limit is going to be the square root of this limit, right? So this is the square root of 4, which is 2. So I want to walk through and point out what I did here. So, and keep in mind, this trick is really, really handy. I needed to get this denominator inside the root. And since it was a square root, I decided that I could just square it and put a square root on it, because when it simplifies, it comes back down. Notice you can do the same thing. And actually, if you're using a cube, you don't have to worry about the absolute value, which is kind of nice also. And so once we had that trick and I got it joined into one single rational expression, I could just take the limit of the rational expression and then square root everything else overall. Okay, so there was a lot of tricks in there, but the biggest one is the one we just used, this last trick of multiplying by 1 over the highest degree. Excuse me. Okay. So that's what I wanted to get through today. There's a lot of algebra in this one. So, there's going to be little places you get hung up. If you don't, that's awesome. But if you do get hung up, talk to your classmates, talk to me. I'm more than happy to give you help. And I know your classmates are more than happy to find people to actually work with too. So once again, until next time, keep your pencils and your wits sharp.